Can I start?
Yeah. Well, wait, hold on.
Yeah.
So this might be, I'm going to be timing. Have you timed it out?
Yeah, more or less.
Okay. Do you want like some sort of a warning?
Yeah, maybe like a 2-minute warning.
Okay. I'll give you a 2-minute warning.
Okay.
And it'll be loud when it goes off.
Okay.
All right. Good.
All right, so my name is Nick, and my project is embedded sensor processing for personalized physical therapy. And my mentor is Venki. So the main question that I was investigating was, how can new personal technologies expand access to healthcare, specifically for remote physical therapy and recovery after injuries? And so the design of this, when I started thinking about this problem, I looked at kind of like what has been done so far. And one of the main things I saw was different camera technologies. And I found that they've proven challenging when they're used to provide accurate measurements for flexion and extension, and for gathering information describing more than two axes. And so my approach used a sensor, like a wearable sensor, where a gyroscope and an accelerometer on a microcontroller collect data time series for 3 axes, so you get a little bit more information to classify motions. And so the purpose of this project is to propose a system to detect mistakes in motions of physical therapy in order to then give feedback to a patient to improve their form. And kind of what's unique about this solution is it aims to incorporate local processing in order to give feedback in real time, so you don't need to stream data to the cloud or stream data to a laptop or anything. And so this is kind of like a significant new field in wearable devices. So this is a demo, and I have 2 demos, but I'll only show one right now. The first one is detecting just what exercise is done, so like a front squat, a back squat, or something. And the second demo, which is right here, which I'll play right now, is actually detecting mistakes in squat, and then it gives feedback on that mistake. So I'm going to put it on 1.5 speed, and we can watch. So this is the training phase where I train a bunch of different movements, and the sensor kind of like learns the mistakes. So for example, that was an incorrect squat because my knees went far over my toes. This one, my knees buckled outwards. That's incorrect as well. This one, my knees buckled inward, so that's also incorrect. So after the training phase, this is the testing phase. So I repeat the same movement, and it recognized that that was a shallow squat, and so it gives feedback, try to squat deeper. The next one, the mistake I made here was my knees were too wide, so it tells me don't buckle your knees outward. This one, my knees, again, went over my toes, and the system detected, based on the previous training, that it was closest to the one where the knees went over the toes. And this one, my knees buckled inward, and so it tells me don't buckle your knees inward. And finally, we get to the point where I do a correct squat. So the way the system works, this is continuous motion detection using a data time series. So there's 2 different phases like you saw in that video. There's a training phase where specific exercises are collected as kind of template motions. In this case, I trained different mistakes or predefined errors in the motion, but they don't necessarily have to be. These can also be done once every session, or they can be pre-stored on the device and kind of used across all sessions. Once the training happens, then there's test motions, so the patient now repeats the exercises at home. And the sensor collects a data time series and then computes the cross correlation to predict which template it's closest to. And then based on which motion was likely predictive, we can give advice to the patient in order to change their form on the next repetition. So basically the mathematical process of how I'm comparing the test motion versus the template is something called cross correlation. And it's the measure of the similarity of 2 series as a function of the displacement of one relative to the other. And this is essentially just computing the dot product between sample values and the time series. And so you can see here on the screenshot to the right, for the test number 1, it compares the cross correlation to template 1, 2, 3, and 4. And it finds that it's most correlated to template 1, so we can predict that template 1, that motion 1 was actually done. And I originally started this project using a convolutional neural network to classify motion events, but I found that for the case of continuous motion, this cross-correlation was actually the best tool. Some obstacles that I had in developing this project were kind of two main things. One was with collecting data, and the next was with like analyzing data. And so for collecting data, I found that there was some noisy data that led to inaccurate measurements. So for example, when the patient is motionless and hasn't really started any movement, my device was reading a rotation rate, like just like some drift. And so to fix this, I basically measured an initial offset before training. I told the user to like stand in a motionless state. I measured this offset, and then for each recording after that, I basically subtract that and take it as an offset. So it basically compensates for this extra recording. The next obstacle was detecting the start and stop of a movement, because after the patient does a movement, they might be shifting around a little bit, or they might be adjusting, and I don't really care about this movement. I only care about the exercise itself. And so to solve this, I created kind of like a threshold amplitude of rotation from the gyroscope reading, and then every time I checked, if the reading went below this threshold for more than 1 second, I would stop measuring. And so this really helped to kind of isolate, collecting only data for the exercise itself and not extra random stuff. So once I got a little bit better at collecting the data, and for analyzing the data, there were a few problems I ran into. The main thing being with just the nature of the cross-correlation. I found that for exercises and movements that are very short, so like a shallow squat or something that's like very short, the cross-correlation technique was a lot less accurate. And I found that there's much better performance when we had more complex movements. The reason being is that for a longer data time series, there's more artifacts or unique data structures. So when you do the cross-correlation, you'll get a higher correlation because there's more points to compare to. So that's one thing I kind of had to keep in mind when designing it. For results, I detected deviations from acceptable bodyweight squatting technique with a little bit less than 70% accuracy. If I did a bunch of trials, it was around like 70%. The video I showed, I kind of picked out like when it worked four times, but that wasn't always the case. And so in general, this cross-correlation technique did not entirely provide the precision I was hoping for. And the biggest thing was for similar movements that have data artifacts that resemble one another. However, it did show a lot of promise. For example, in my demo 1, which I didn't show, it did a great job at determining what exercise, if the exercises were very different from each other. But for for a squat where the mistakes can be like very similar with each other, sometimes when you do the cross correlation, you can't really tell which event happened, so it's a little bit more convoluted. And so maybe a solution to this is multiple sensors may be needed. So you combine data from 2 sensors, or a different approach for cross correlation. So those are some ideas of how I could build on that. And then, like I said, the proposed system is great at detecting what exercise was done, as seen in demo 1, but it would need a little bit more work to get a higher accuracy of error analysis attempted in demo 2. And yeah, that's pretty much it. So I'd like to thank STM Microelectronics for the tutorials. That's kind of like the hardware that I used, Professor Kaiser at UCLA, the IRI team, and my mentor, Venki. Thank you.
Very good.